Hi everybody, Augie Kennedy here, back again with some more super awesome calculus. So we're still on chapter 3, entitled Differentiation Rules, and today we're going to go over related rates, which is a concept that causes a lot of worry and fear among a lot of people interested in math. But before we do that, let's go over the big problem from last time, which was an exercise in logarithmic, in the differentiation of logarithms. So, if we remember, the big problem was I asked you to find y and y prime of y equals x squared times the natural log of 2x. Okay? So let's go ahead and let's write this out. Y equals x squared times the natural log of 2x. Now, immediately looking at this, you should recognize a couple things. First of all, you've got a product here, so you're going to be using the product rule. The second thing is that you don't have the natural log of x, you have the natural log of 2x. So we're dealing with a composition of sorts, which means we're going to use the chain rule as well. So let's see the way this works out. Remember, the product rule is the derivative of the first times the second plus the derivative of the second times the first, or vice versa. So let's do it this way. Derivative of the first is 2x times the second ln 2x plus the first times the derivative of the second. Now, the derivative of the second, we know that the derivative of ln x is 1 over x. But we know that the derivative of the inner part, because of the chain rule, is going to be 2. So, what we end up getting here is x squared times 2 over 2x. Now, what this means, and what this is going to do, is we're going to therefore get, over on this side, 2x squared over 2x. And with that, we know that these are going to cancel and reduce, and we're going to be left with x. So really, the derivative of the second part of this product rule is just x. So there you go. Y prime equals 2x times the natural log of 2x plus x. Now, let's take y double prime, the second derivative. Well, we're going to do the same thing, except we also have a sum rule to include with the product and the chain rule again. Let's take the product rule again. Derivative of the first, 2 ln 2x. That was very easy. Plus 2x times this derivative. We already know it's going to be 2 over, what? Yep, 2x. And we can see that these are going to cancel. The 2x's here are going to cancel, and we're going to be left with 2 plus the derivative of x is 1. So if this is 2 and that's 1, that means that y double prime equals 2 times the natural log of 2x plus 3. Hopefully you can see how that works. That's that's how you take the derivatives of logarithms. It's not logarithmic differentiation, which we also covered, I believe, in the last lecture as well. So on to related rates. Related rates are a concept that we actually didn't go over in calculus class, but I know that a lot of calculus students really, a lot of calculus teachers focus on this type of problem, and a lot of students need some help with it. So I'm going to go over 3 examples from the book that I think best illustrate the concept of related rates. The general idea is that you're given a piece of information. Like, for instance, we're going to be doing an exercise with a balloon is growing at a certain, its volume is growing at a certain rate, and we want to find out what rate its radius is growing. Or, for instance, you got a ladder up against a wall. Well, as the bottom of the ladder slides out, we want to find out how the top of the ladder slides out. Those are questions regarding related rates, and we'll be looking at some examples of those. So the first one is, it's going to be kind of tricky to just word this. If I can, in post-production, I'll put the actual things for you to read, but here's the question. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, well, the first thing we're going to want to do is we're going to have to ask what the problem is really asking. What's it asking? It's telling us that air is being pumped into a balloon. So I like to draw things. I'm a terrible artist, and it's okay if you are too. That's not the point. The point is to just get it out there. So a spherical balloon that's close enough to a circle. Okay? A spherical balloon, and its volume, we know volume is increasing plus at 100 centimeters cubed, at 100 cubic centimeters a second. How fast is the radius expanding at 50 centimeters? Okay? Now this is a very typical related rates problem. We have volume, we need radius at a certain size. So what we need to do here, the way to do this is to set up a related differential rate. So we know here that what is this actually saying? Volume is increasing at 100 centimeters cubed per second. Sounds to me like it's a change, a rate of change, which is exactly what it is. It's a change in centimeters cubed over change in seconds. So it's the change in volume. We could say that this is the change in the dV, we'll let volume equal V, over the change in time, which we'll call dt. And we want to know what the radius is doing, how it's behaving at 50 centimeters. So what we're looking for here is we're going to see if we can relate this dr to dt. So this is the general framework. We know that dV dt equals 100 cm cubed per second. We want to know what dr dt is at 25 centimeters. Because the diameter is 50 centimeters, the radius is half the diameter, so diameter 25. Now, let's erase this little picture here, because we don't really need the picture here, but we do need our information. dV dt equals 100 cm cubed per second. dr dt, we don't know. We want to know it at 25 centimeters. What do we know about volume, though? How can we relate volume to radius? This is where the fun of a related rates comes in. Because you kind of have to know your geometric formulas and the way shapes relate to one another. We have volume linked with time, radius linked with time. How can we link volume and radius? Well, if you remember, volume of a sphere is none other than this formula. Volume equals 4/3 pi r cubed. And if you didn't know that, that's okay, because you know it now. And you might, taking this information, have some idea of what to do next. What we're going to do is we're going to differentiate this. We're going to differentiate this. And here's how we're going to do it. V equals 4/3 pi r cubed. What would the derivative of V be? What would V prime be? Well, this isn't too hard. Pi is just a number, so it's going to be V prime equals, take the power rule here, r cubed It's going to be 3 times 4/3 pi r squared. And you'll see that the 3's cancel, and we get 4 pi r squared. That's v prime. Now, check this out. dv dt, therefore, equals dv dr dt equals 4 pi r squared dr dt. We now have both of the rates we want to relate to each other, and we know what dv dr is. So, now that we have that, if we know that dv dt is just this chain rule here, dv dr dt, radius with respect to time, and the volume with respect to radius, we know that the volume with respect to radius is 4 pi r squared because we differentiated it right here, and we're multiplying times dr dt. Now, what comes next? Well, we need to isolate dr dt because that's what we have to know now. We know dv dt, let's isolate dr dt. So, we have dv dt equals 4 pi r squared dr dt. All we need to do now is divide by 4 pi r squared. So we have dv dt times 1 over 4 pi r squared equals rate of change of radius with respect to time. And now we can finally plug in what we know. We know that the radius we're looking for is 25. Okay? R is 25. And we know that dv dt, we already know this information from the problem, is 100 centimeters cubed per second. So let's plug it in. dv dt equals 100 times 1 over 4 pi times 25 squared. You should get 1 over 25 pi. So therefore, the radius of the balloon is increasing at 1 over 25 pi centimeters per second. That's a related rates problem. We're going to do 2 more just so that you can kind of understand a little bit better what's going on here. Here's the second question. A ladder 10 feet long rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? There's a lot about ladders and walls here. Remember how we drew a circle last time to represent the spherical balloon? A diagram is really going to help us a lot more here. So let's picture this. We got a wall and we got the ground. Wall, ground. And here we've got a ladder. Okay? And the ladder is sliding away. Now this already, you can tell, this looks like a coordinate plane. We've got y at the wall. We've got the ground is x. What else do we know? Well, we know that the ladder is 10 feet long. So the ladder is tilted, but it's 10 feet long. Okay? And it's sliding away from on the bottom at 1 foot per second. And we want to know how fast the top is sliding at 6 feet from the wall. So, first thing we know is we can look at this. We know that we have dx dt. dy dt, we don't know. We want to know dy dt. We want to know the change in y with respect to a certain time. We understand that we want it with respect to time because dx is related to time, feet per second. So that's dx dt. Well, we want to know dy dt. So the way we're going to do that is we need to relate all of these things together. Now, it's no coincidence that I drew this picture like this because you can see that this makes a right triangle. So we already know how all 3 of these things relate to one another. It's the Pythagorean theorem. The ground squared plus the wall squared is going to equal the height of the ladder squared. So that's x squared plus y squared equals 10 squared, or 100. So, now what we have is we have an equation to work with, which is a little bit more useful. X squared plus y squared equals 100. And now what we're going to do is we're going to differentiate with respect to time. 2x squared is going to be 2x, but we're differentiating not with respect to x, not with respect to y, but with respect to t. So just like when we used implicit differentiation, now we're going to have, we had those little dy dx's. Well, now we've got dx dt plus y squared. Well, we know that's going to be 2y, but remember, once again, differentiating with respect to time. dy dt equals, the derivative of 100 is 0, because the derivative of any constant is 0. So now we're kind of seeing what we've got. We need to relate dy dt to dx dt, and it's going to be very easy to do, because all we need to do now is set it up so that dx, 2x, I'll write out the steps, dx dt equals negative 2y dy dt. Okay, and now we're going to divide by 2y, and we're going to get 2x over negative 2y dx dt equals dy dt, or more simply, negative x over y dx dt equals dy dt. I'm going to erase this and write that up there. If you hope you could follow those steps, negative x y dx dt equals dy dt. We just differentiated the whole equation there with respect to time, and we need dy dt because we know the rate of the ground, we need the rate of the wall. So, negative xy, well, what do we know? We know that x is going to equal 6, because that's how many feet from the ground, so x equals 6. And the Pythagorean theorem that we wrote earlier would yield y equals 8. Because you have a 3, 4, 5 triangle, and you also have a 6, 8, 10 triangle. So 6, 8 times dx dt, which is, or negative, so we have negative 6 eighths times dx dt, which is 1 foot per second, so times 1, equals dy dt, which is negative 3/4 of a feet per second. It's going to be the same feet per second as was in dx dt. Just to go back over this Pythagorean review, we had x at the ground, y, and 10. Okay? The only thing, if x is 6 feet from, if x is going to equal 6, then y, and the other side, and the hypotenuse is 10, then the only thing y can equal, if you solve the Pythagorean theorem, is 8. That's why y equals 8. Okay. So, there's your answer. We're going to do one more really fast because I'm hella low on time. Here we go. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? This is a sucky sounding question, but we can make it a little bit less sucky. Let's picture, a man's walking, alright? And a searchlight is 20 feet away from him and it's kept focused on him, so it's going to be turning. It's going to be rotating. Anytime you get something like that, you're pretty sure you're going to be dealing with triangulation and sine, cosine, tangent type things. So here's the guy. He's chilling, he's walking this way. Alright? And over here is the searchlight. There's the searchlight. It's focused on him. Guy starts here. He's going to walk out to here because he's going to walk, and we know that this is 20 feet away. And here's X. At what rate is the spotlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Well, we know a straight line, the shortest distance between 2 points is a straight line. So the closest he was to the searchlight was right in a straight line from it, which was 20 feet away. So 15 feet away from that point would mean x equals 15, right? Okay, so we know that. We know two sides of this then. Now, we also know that dx, we know this is angle theta. It's not necessarily, we know, what else do we know here? We know that dx dt is 4 feet per second. Alright, so we're obviously going to probably want to find dy dt, right? No, because we want to know something about the rate of the angle. So, we need to find d theta, that's that angle right there, with respect to time. Now, how are we going to do that when x is 15? Well, here's how. If you took in all of that information, we know that dx dt equals 4 feet per second. And we know that d theta dt, or we would need to know d theta dt at x equals 15. How do you relate x to theta? That's the question. Well, we had this triangle here. We knew x is here. Alright, so we have opposite, and we have adjacent is 20. Opposite is x, 20 is y. What's opposite over adjacent? Well, we know SOHCAHTOA, tangent, T-O-A, tangent is opposite over adjacent. So tangent of theta is x over 20, opposite over adjacent. Or x is 20 times the tangent of theta. So, we differentiate both sides. X equals 20 tan theta is what we have. X equals 20 tan theta. Let's go ahead and differentiate dx dt. Because remember, differentiating not with respect to x. That's why it's not 1. It's technically 1 times dx dt. Equals 20 secant squared theta d theta dt. Secant squared theta, that's disgusting. But remember, I like to do everything with sine and cosine. So secant is 1 over cosine. So dx dt, or d theta dt, we'll just get to the shortcut here. D theta dt is 1/20th times cosine squared theta dx dt, or 1/5 cosine squared theta. And if you plug in theta equals 4/5, you then get 1/5 times 4/5 squared. Cosine theta is 4/5 because the length of the beam is 25. You get 16 1/25. I'm sorry I had to run through that one, but we're way over time. So I'm going to go ahead and leave you with the big problem. You can work this out on your own. A cylindrical tank with radius 5 meters is being filled with water at a rate of 3 meters cubed per minute. How fast is the height of the water increasing? Well, go ahead and figure that out, and we'll see you next time. Bye-bye, y'all.